Hi and welcome to another edition of Calculus 2. Today we are going to talk about examples of integration by parts that we called as self-referral. Let's go ahead and see what this story is about. So two example problems here I have for you. First one, exponential of ax cosine of bx, and the other one, secant cube of x. We mentioned previously that this is an integral you see very often in circuit classes, Laplace transforms, lots of places where you're solving certain equations, differential equations, this kind of things comes up. And in fact, there are perhaps as many as half a dozen different methods of actually finding this integral. So it's good to have a coverage of all the possible approaches, and what we are learning here is integration by parts. You might see some other places Euler formula or methods from Laplace transforms and such. So let's see, just a quick review. So we are going to first approach exponential of a is some number and b is some other number. So we just leave it as a and b so that our formula works for many cases. Let's just remind ourselves what was our integration by parts formula. We said it's same as product rule, really written in reverse. So that is our standard way of dealing with this thing. In this problem, it so happens that you kind of cannot go wrong. So for example, I take u to be exponential of ax, and you said as soon as you pick one of them, the other one is decided for you. Whatever is left is the other one. Cosine of bx dx. Then we come to du. Derivative of this is a exponential of ax dx, of course, and v will be antiderivative of this. That's going to be, of course, let me see if we can pause for a second and ask the audience, what is the antiderivative of that cosine of bx? You're finding something whose derivative is that. So what is that? That is sine of bx over b. Okay, with that in mind, what we have is going to be u times v. So I'm going to have exponential of ax times v, which is sine of bx over b, then minus integral of v, which is sine of bx over b, times du, which is a exponential of ax dx. Let's rewrite this thing a bit more civilized fashion. So exponential of ax sine of bx over x over b. A over b, I can take it outside because these are constants, and now I have exponential of ax sine of bx. We see an interesting play here. We want ax cosine of bx, we end up with ax sine of bx. It looks like we change sides and we haven't gained anything. The interesting thing is that if we go ahead and do this thing all over again with respect to this problem, exponential of ax sine of bx, and process it, we are going to come back to cosine of bx. At the first sight, it might look like we are stuck in a cycle and we're not going to get out of it. But in fact, we are going to have this expressed in terms of itself. That's why it's called self-referral. The integral is going to be connected to itself, and that's going to be essentially the thing that's going to give us the final value. So let's go do it again and focus on this thing. So I'm going to make some room for coming back here and completing the problem. So we are going to pick this. So let's make sure these don't run into each other. So I have exponential of ax sine of bx dx. By now we know the drill. Same thing as before. dv now changed to sine of bx dx. Therefore du same as before. So notice that we are recycling a letter. This the v means something else now. Otherwise you have to go every time dig out some other pair of letters and play with them. So this is a dv, that's another dv. So du as before, aex dx, and v, what's the antiderivative of sine of bx? Again, let's have the audience participate. What is the antiderivative of sine of bx? So maybe a picture, perhaps a retirement place picture is going to excite you to get this thing done. Okay, so this is going to be minus, didn't get that wrong, huh? Cosine of bx over b. So when we write this thing, then I'm going to have u times v. Let's put it nicely at the beginning, minus ex cosine of bx over b. And then we said v du, I have to multiply these things and subtract, and let's see, maybe I write it first full force and then we come back and simplify. Let's write v, so that is minus cosine of bx over b, and then du, that is a exponential of ax dx. I put them in parentheses so I don't make a mistake with subtractions. Let's clean up, minus exponential of ax cosine of bx over b, and minus makes a plus. A and b are constants, I can put it outside, and then I have exponential of ax cosine of bx dx. So what is interesting, we are starting with this integral, ending up again with another integral, but notice this is the same as what we wanted. That's not a bad sign, that's actually a good sign. Let's see how does that help us. So I go ahead and rewrite this thing again, exponential of ax sine of bx over b. Then I have minus a over b of this. That integral is this. So I'm going to write it. It's minus exponential of ax cosine bx over b of plus a over b integral of exponential of ax cosine bx dx. Let's expand this thing. So I'll have exponential of ax sine of bx over b, and here I have a over b squared of exponential of ax cosine of bx, and then minus a over b times plus over a b is going to be, well, corrected, minus a squared b squared of integral of eax cosine bx dx. So what I'm going to do is to take this thing next to this integral, because they're the same, and factor this integral itself. So there's one of them here, minus a squared plus over b squared on this side. When I take this to left, it becomes positive, and so I'm going to have this integral on the left is going to have 1 plus a squared b squared eax cosine bx dx. On the right hand side, I go ahead and take the common denominator of these two, Common denominators, of course, just a b squared, and I'm going to have ex sine bx and times a b here, and then eax cosine bx and then there's going to be a constant. I'm going to take care of my constant after I'm all done. Any indefinite integral is going to have a constant. I am going to put that at the very end. Okay, the left hand side, let's do it the following way so I can squeeze everything here. So in the left hand side, I just take a common denominator, it's b squared, and here I'll have a squared plus b squared. So I'm going to take the right hand side, divide by the coefficient of the left hand side, and out comes the following: integral of exponential of ax cosine of bx dx. B squared and b squared cancel out, that comes in the denominator. So I'm going to also on the numerator factor exponential of ax to make it less cluttered. I'm going to have a cosine of bx plus b sine of bx, all of that divided by this factor of a squared plus b squared. And then we said, okay, we have this antiderivative, and then we just throw in a constant for good measure. That will be the answer to our problem. So we have this. It was a bit twisted, yes, but here an exercise for you. Try to go from scratch and find out what this one would be. Okay, and another approach that you can take for either of these problems is that ladder method or the tabular method that we talked about last time. But since we have so many other things to do, let's move on to another example. So we said that we want to do example of secant cube as well, one of the rather intriguing integrals. So let's see.